Imagine launching the fastest spacecraft in history, yet waiting nearly a decade for it just to snap one photo of Pluto. And even that's nothing compared to our real cosmic obstacle, the impossible gap to Proxima Centauri. What if something out there isn't just distant but fundamentally unreachable by design? In 1964, a young aerospace engineer and Caltech graduate student named Gary Flandro made a discovery that would change the course of space exploration forever. While working at NASA's Jet Propulsion Laboratory, he calculated that in the late 1970s, the outer planets Jupiter, Saturn, Uranus, and Neptune would align in a rare cosmic configuration, an event that would not occur again for 175 years. This planetary alignment opened a once-in-a-lifetime window for a mission that could visit all these distant giants using gravity-assist maneuvers, where a spacecraft slingshots around a planet, gaining immense speed without burning fuel. Flandro realized this could cut travel time from Earth to Neptune from 30 to 40 years down to just about 10. Encouraged by this, NASA began planning an audacious mission called TOPS, with 4 space probes designed to visit every one of those planets in sequence. However, the project quickly encountered fierce resistance within NASA itself. Top priorities at NASA were manned spaceflight and the upcoming Space Shuttle program. Automated robotic missions to the outer planets ranked low on the budget list. Despite support from key figures like Wernher von Braun, who advocated for the heavy-lift Saturn V rocket to launch the mission, NASA headquarters was hesitant. Several officials actively tried to block or delay the mission, fearing costs and technological risks. Buddy groups inside NASA doubted if the spacecraft could survive the asteroid belt or the harsh Jupiter radiation environment. Gary Flandro himself encountered skepticism from experts who insisted the navigation wouldn't be precise enough and communications would fail over such vast distances. "You just can't do that," they said. But Flandro persisted. Eventually, the mission was drastically scaled back to just 2 spacecraft, which became Voyager 1 and Voyager 2, launched in 1977. These probes were built secretly with the full Grand Tour capabilities envisaged, despite the official cuts. Voyager 1 had a trajectory that could have included a flyby of Pluto. But in a pivotal decision, NASA redirected it to investigate Titan, Saturn's enigmatic moon, considered a higher priority target. Pluto, once again, was passed over and left waiting decades for its own mission. Why was Pluto dismissed? Some say it was because Pluto was reclassified as a dwarf planet, seen as less important than the giant planets. Others suspect political and budget limitations played a role in shaping mission priorities. Conspiracy theories even whisper about hidden factors we may never fully uncover. Meanwhile, the detailed exploration of Jupiter, Saturn, Uranus, and Neptune by Voyager revolutionized planetary science and gave us stunning new knowledge. But Pluto remained humanity's great elusive mystery on the edge of the solar system. What if Voyager 1 had visited Pluto? How much sooner would we have seen its icy mountains, frozen plains, and mysterious atmosphere? Would early data have changed our understanding of this distant world, or revealed secrets that some preferred to keep buried? The story of this missed opportunity is one of human ambition and bureaucratic friction, a tale of a cosmic window that almost slipped shut. Yet this chapter set the stage for one of the most thrilling space missions of the 21st century, New Horizons. What happened next was even more shocking. After the Grand Tour's success with Voyager, one would think Pluto was next in line for exploration. But the reality was far more complicated. For decades, Pluto was stuck in limbo, a destination everyone wanted to reach, but no one could quite afford or commit to. In the 1980s, a passionate group of scientists and engineers, including Alan Stern and Fran Bagenal, formed what was called the Pluto Underground. This informal alliance was inspired by a similar movement for Mars exploration and aimed to push Pluto from a neglected afterthought to a priority target. They lobbied NASA aggressively, writing letters, proposing mission concepts, and preaching the scientific value of studying Pluto and its largest moon, Charon. NASA started serious studies. Early mission ideas included tiny, ultra-light spacecraft aiming to reach Pluto quickly, like the ambitious Pluto 350 mission. The idea was to design a lightweight probe, around 350 kilograms, that could slash travel times and reduce costs. But these concepts sparked controversy within NASA. Some experts called the smaller designs too risky, fearing that minimalist spacecraft might lack critical instruments or fail altogether. Funding was another enormous hurdle. Launching such missions required powerful rockets like Titan IV, carrying price tags of around $400 million per launch. Budgets tightened in the 1990s, and proposals ballooned. Pluto 350 slowly gave way to larger, more ambitious missions like Pluto Kuiper Express, a planned flyby of both Pluto and other mysterious Kuiper Belt objects beyond. However, despite progress in mission planning, Pluto Kuiper Express suffered a cruel fate. In 2000, NASA abruptly canceled the project, citing budget overruns and shrinking funds for outer solar system exploration. The decision sparked outrage among planetary scientists and the public alike. This cancellation galvanized the Pluto Underground and groups like the Planetary Society to step up pressure. Their campaigns highlighted Pluto's scientific importance and the value of exploring distant worlds beyond Neptune's orbit. Conversations inside NASA began shifting, and a compromise was found. NASA created the New Frontiers program, a new class of medium-cost missions aimed at bridging the gap between massive flagship missions and smaller discovery missions. New Frontiers opened the door for Pluto to finally get the space probe it deserved. These struggles underline how difficult interplanetary exploration truly is. Scientific curiosity clashes with political reality and budgets, and distant targets like Pluto often fight an uphill battle for attention. But Pluto's time finally came with New Horizons, ushering in a new era of discovery and wonder. After decades of frustration and dashed hopes, NASA finally launched a mission that would change everything. New Horizons. On January 19, 2006, atop an Atlas V rocket, New Horizons blasted off from Cape Canaveral like a comet, becoming the fastest spacecraft ever launched from Earth, hurtling towards the outer solar system at over 36,000 miles per hour. The stakes were enormous. Pluto, once the 9th planet and now known as a dwarf planet, was still a complete mystery. The spacecraft had to perform flawlessly during a journey of over 3 billion miles, more than 9 years in the dark, speeding through the void of space, before it could send back a single, clear image. To shorten the trip, New Horizons used the gravity of Jupiter to slingshot itself faster. In February 2007, it swung past the gas giant at incredible speed, gaining a boost that cut months from its journey. It was a high-risk, high-reward maneuver, and the first full test of its instruments happened during this flyby. After Jupiter, the probe entered hibernation, a kind of deep sleep to conserve power and reduce wear on its systems as it drifted farther and farther from Earth. This state lasted for nearly 8 years, broken only by brief wake-ups for system checks and planning. As the spacecraft neared Pluto in late 2014, mission controllers brought it back online. From January 2015 onward, New Horizons began a detailed observation campaign, capturing images that quickly surpassed the clarity of even the Hubble Space Telescope. Then came the climax. On July 14, 2015, New Horizons made its closest approach to Pluto, passing within 7,800 miles of its surface at speeds close to 30,000 miles per hour. During a tense 22-hour radio silence, the probe focused entirely on mapping Pluto and its largest moon, Charon, capturing stunning images of mountains higher than the Rockies, vast glaciers, and a surprisingly young surface hinting at geological activity. The spacecraft's 7 scientific instruments worked in perfect harmony, from Ralph's visible and infrared imagers to Alice's ultraviolet spectrometer analyzing Pluto's thin atmosphere. The data revealed a surprisingly complex and dynamic world, with signs of ice volcanoes and evidence of a possible underground ocean. Scientists were stunned. Pluto was much more than a cold rock in the outer solar system. It was a world full of mysteries. The images began to arrive on Earth slowly, due to limited bandwidth. It took over a year to receive all the data, but each new revelation rewrote textbooks and fueled debates in the scientific community. After completing the flyby, New Horizons set off to explore other distant objects in the Kuiper Belt. In 2019, it made history again by flying past the small, oddly shaped object Arrokoth, giving humanity its first close look at a primordial building block of the solar system. The success of New Horizons was not just a technological triumph, but a symbol of persistence against all odds, years of setbacks, debates, and budget cuts. It proved that even the most distant, cold, and mysterious corners of our solar system could be unlocked by human ingenuity. But the journey continues. As New Horizons ventures deeper into the Kuiper Belt, it carries our hopes and questions forward, reminding us that in the vastness of space, the end of one mission is just the beginning of another. After conquering the outer edges of our solar system with New Horizons, one might wonder, what about the stars beyond? The closest star to us, Proxima Centauri, lies a staggering 4.24 light-years away. That's about 25 trillion miles, or 40 trillion kilometers. To put it simply, it's unimaginably far, so distant that reaching it challenges everything we know about space travel. Our fastest spacecraft so far, Voyager 1, launched in 1977, travels at about 38,000 miles per hour, about 17 kilometers per second. But even Voyager 1 would take roughly 76,000 years to reach Proxima Centauri. To put this into perspective, humans emerged only about 200,000 years ago. We might be launching future explorers who wouldn't arrive until many millennia after Earth is unrecognizable. This immense timescale raises immediate questions. How could humanity ever send missions to another star within a human lifetime? What technology would be required? And what obstacles would such a mission face? Currently, chemical rockets, the workhorses of spaceflight, are simply not nearly powerful or efficient enough for interstellar trips. Fuel requirements grow exponentially, and the harsh environment of deep space adds layers of technical complexities. Beyond speed, there are other brutal challenges. Cosmic radiation bombards any craft traveling through interstellar space. Tiny grains of dust, moving at near-light speeds, could destroy unprotected spacecraft. Communication delays stretch to years. Any messages sent or received would take more than 4 years one way. Scientists have been investigating alternative propulsion concepts. Nuclear propulsion, ion thrusters, and plasma engines like VASIMR, Variable Specific Impulse Magnetoplasma Rocket, could, in theory, provide higher speeds and sustained travel capability. But even these advanced ideas fall short of the goal by a large margin. One of the most visionary projects is Breakthrough Starshot, announced in 2016. This ambitious plan proposes launching thousands of tiny nanosats, each equipped with light sails. Powerful laser arrays from Earth would push these sails to speeds of up to 20% the speed of light, roughly 186 million miles per second. At such blistering speeds, a tiny spacecraft could reach Proxima Centauri in just 20 to 30 years. But this raises new questions. Could such fragile nanosats survive the intense laser acceleration and the dangers of interstellar space? And would we even be able to send usable data back to Earth over those distances? While the futuristic technology paints an exciting picture, it also invites a sobering reflection. No human has yet traveled beyond the moon. No probe has left the solar system with the intent to reach stars nearby. Our dreams of interstellar travel remain tantalizingly out of reach. Some wonder if the universe itself raises invisible barriers, scientific limits, or unknown cosmic phenomena that keep us confined to our solar neighborhood. Could there be reasons, natural or even intentional, why no one has successfully ventured to another star yet? As we develop new propulsion methods and test the boundaries of our knowledge, Proxima Centauri stands as both a beacon and a challenge, a reminder of how far we have yet to go and how much we have yet to learn. And in that challenge lies the essence of human curiosity, the drive to reach further, to know more, and perhaps someday to cross the final gulf. If reaching Proxima Centauri with today's rockets is unimaginable, what about tomorrow? Humanity's future in interstellar travel hinges on new propulsion technologies. Ideas once relegated to science fiction are now under serious study. One promising avenue is electric propulsion, such as ion drives and Hall thrusters. These work by accelerating charged particles to generate thrust with fuel efficiency far beyond chemical rockets. For example, the VASIMR plasma engine aims to reduce travel times in the solar system drastically. It can potentially adjust thrust and efficiency during flight, a major leap over fixed chemical propulsion. But even electric drives rely on carrying fuel, which limits their ultimate speed and range. That's why nuclear propulsion grabs so much attention. Concepts like nuclear thermal rockets, which heat propellant via a nuclear reactor, promise greater thrust and efficiency. More ambitious yet is nuclear pulse propulsion, exemplified by the Project Orion concept from the 1960s, where tiny nuclear bombs would propel a spacecraft forward with massive bursts of energy. However, such nuclear methods face enormous technical, environmental, and political obstacles. Launching several nuclear explosions through space is terrifying to many and fraught with legal complexities, even if it could theoretically reduce interstellar trip durations from tens of thousands to mere hundreds of years. Then there's solar sail technology, using massive, ultra-thin reflective sheets to catch the light pressure of the sun. Solar sails are propellant-free and could accelerate continuously. The Japanese Icaros mission showed the concept's viability, but speeds are limited by sunlight intensity and demand vast deployment areas for meaningful thrust. Enter Breakthrough Starshot, perhaps the boldest concept of all. Proposed by physicist Philip Lubin, this initiative involves launching swarms of chip-sized nanocrafts equipped with ultra-thin, reflective light sails. Powerful Earth-based lasers would fire intense beams to push these tiny probes up to 20% the speed of light. At these velocities, the probes could reach Proxima Centauri in just 2 decades. Imagine. But turning this dream into reality involves monumental challenges. Manufacturing sails that can withstand high-energy laser pulses, surviving interstellar dust and radiation, miniaturizing scientific instruments to microscale, and transmitting data back to Earth with incredibly faint signals. Despite the hype, recent reports reveal the program still faces serious hurdles in funding and engineering. The best-laid plans can be stalled by practical realities. Beyond these technical ambitions, some voices whisper about more speculative possibilities. What if beings or cosmic forces guard these frontiers? Ancient myths and modern conspiracy theories speculate that extraterrestrial civilizations might not want us to reach neighboring stars, or technology to slow our progress for reasons unknown. Others suggest hidden physics yet undiscovered. Natural laws or quantum barriers may impose hard limits on how fast matter can travel or communicate across vast distances. Whether wild or real, these theories fuel debate and inspire hope. They remind us that space exploration is not just an engineering challenge, but an intellectual and philosophical frontier. For now, our spacecraft continue to push deeper into the unknown, carrying the human spirit with them. Pluto and Proxima Centauri are more than distant points in space. They are monuments to human curiosity and resilience. Each mission teaches us just how far ingenuity can push the boundaries of the unknown. Yet, the vastness of the cosmos reminds us there will always be new horizons, new mysteries waiting just beyond our reach. If these cosmic puzzles left you wanting more and questioning what lies beyond what we know, then stay close. The next journey we'll uncover will challenge everything you thought was possible. Don't miss it.